we are going to first look at some trig equations.
Okay. Can I ask you to do one thing?
Yes, sir.
Back up a little bit from your microphone. It almost sounds like if I talk right on top of it. That's what it sounds like, kind of?
Yes, sir.
See if you can back up and see if that doesn't help a little bit. Okay, what are we going to do again? I might be too far back. I can't hear anything now. Hello? You're cutting in and out a little bit. Almost like the cable isn't secure or something.
Trig equations.
Okay, trig equations. Give me a trig equation. Let's solve it.
The tangent of x plus 1 is equal to 0.
Okay. Pretty much want to solve these just like you would an algebraic equation up to a point. So what would I do if this were an algebraic equation?
Subtract 1 from both.
Okay, so I get now, remember one thing, that we're always taking trig functions of angles.
Yes, sir.
If we're trying to solve for x, we're going to have to take the inverse trig function of -1.
Yes, sir.
And so essentially, this is what we have. And that's a super important concept in trig. When you're solving for angles, you use inverse trig functions. When you're solving for ratios or numbers, you use trig functions. Now, this gets a little bit, whoops, hold on, I didn't mean to write it like that. I meant to put a -1 in parentheses there. Okay. Now, the real question here is, do they give you a domain with this equation? Do they tell you that x is between 0 and 2 pi, or what?
For this, they say find all the solutions.
Okay. So, the one thing we know, let's talk about this. Tell me which two quadrants where tangent is negative.
Quadrant 2 and quadrant 4.
Okay. And what's the second quadrant angle? Or actually, what's the first quadrant angle where tangent is equal to 1? 45. So 45. What is the second quadrant angle?
135.
And the fourth quadrant?
That is 315.
Now, those are the two answers in the unit circle. But in reality, we know we can add 360 to each one of them. In other words, 495 is also an answer. 695 is an answer. So at this point, I have that one, I have that one, I have that one, and I have that one. And I could keep on adding 360 to each of those answers. Or subtract 360. So actually, I can go all the way from negative infinity to positive infinity with just adding 360 to each of these numbers. Now, how do I represent that? There's a particular way they do it. Tell me if you have seen this, because you wouldn't necessarily have seen it. This is kind of the... And you can use K or N.
Okay.
Where k is all integers,
That's right.
which is positive or negative. Okay. And you still are in degrees, correct? Or have they kind of switched over to radians full time?
Yes, sir. We're still in degrees.
Okay. We'll leave everything in degrees then. But that's the way you do it, is with this kind of notation here.
Yes, sir.
It's a little easier if they ask for just the unit circle. In other words, all the answers between 0 and 360, then you just have to find these two.
Yes, sir.
Now, there is a problem if you use your calculator to get this. Notice what answer you will get if you stick that in your calculator. You'll get minus 45 degrees.
Oh.
That's it. They won't even give you this 135 degree angle, because your calculator can only give you one answer. It has to treat it like it's a function. It can't give you multiple answers like we've generated over there on the left.
Is that because it's using principal values?
Yes. Principal values for inverse tan for a positive number is a first quadrant angle, and for a negative number is a fourth quadrant angle, and more specifically a negative angle. So you'll never get the second quadrant answer out of that calculator. You can come up with it yourself because you know they're separated by 180 degrees, but your calculator doesn't give it to you. And you have to be aware of that. And the same is true with inverse sine, which operates the same way as tan does. In other words, positive values are in the first quadrant, negative values, they give you fourth quadrant, and that negative angles. And the only one that's really different is cosine. Cosine, positive numbers go in the first quadrant, negative numbers go in the second quadrant.
And those are different because sine and tangent are odd, and they have symmetry about the origin, and cosine is even over the y-axis.
Basically, although I think I can give you maybe perhaps a little better explanation. If we look at the cosine function, the whole idea is to come up with the inverse of this and have the inverse be a function. Okay?
Yes, sir.
Well, if I restrict the domain of this function, I'm going to restrict it from there to there, which you'll notice is quadrant 1 and 2. This is quadrant 1. This is quadrant 2. So if I take only that part and invert it, it stays a function, because that blue part only is 1-to-1 both vertically and horizontally.
Okay.
That's what it has to be, is it has to be 1-to-1. Notice that if I do the same with the sine function, it's different. In other words, you take the sine function, and if I go from 0 to pi, that's not horizontally 1-to-1. So if I invert that, I don't have a function. I have to have something that is a function. So what they do is they arbitrarily go from minus pi over 2, notice this is the fourth quadrant, to pi over 2. This is the first quadrant. So all positive ones are in there, all negative ones end up being in the fourth. And tangent works the same way. If you want tangent to be its inversion to be a function, you go from minus 90 degrees to plus 90 degrees.
Yes, sir.
Okay.
And with the solution to that first problem, you showed how you could basically say the angle plus 360 times an integer. If it's tangent, could you do plus 180 times an integer?
Yes, that's the natural period of tangent. Whereas the natural period of sine and cosine is 2 pi, or 360.
Okay, thank you.
Mm-hmm.
Okay, the next problem is 2 times sine squared of x is equal to 1.
Okay. Let's attempt to solve this algebraically first. In other words, our first goal is to get it down to sine x is equal to something.
Yes, sir.
So what's the first step?
Divide by 2, both sides.
Second step?
Take the square root.
Okay, so what do we have?
Sine of x is equal to 1 over root 2.
Almost.
Plus positive or negative.
Because we were solving an equation, every time you solve an equation by taking the square root of both sides, always start your answer with the words plus or minus. And that's going to matter here, you'll notice. Because otherwise, we would have only found 2 quadrants. Now we're going to find all 4 quadrants where this is true. So let's start with the unit circle. First of all, what's the first quadrant where sine is equal to 1 over root 2?
45.
Okay. Second one? We
135.
know it's all 4 quadrants. It's going to cover the plus and the minus. Okay. Now, we also know all multiples of that.
Yes, sir.
Trying to think, there might be an easier way to do this. You usually want to express your answers in the most efficient possible way. And it feels to me like we can do this. Usually that K goes out in front also.
Okay.
In other words, I don't need to express it as 4 different answers. On the previous problem, I believe I did have to express it as 2 different answers. You frequently do. But sometimes with this kind of a solution, I think this covers all of them, both negative and positive. I can't see a solution here that wouldn't be covered by this answer. In other words, this first one is k equals 0. Second one is k equal 1. Third one is k equal 2. Fourth one is k equal 3. And then the fifth one would get you back to 405 degrees.
Yes, sir.
Okay.
All right. The next one is the tangent of x times open parentheses tangent of x minus 1 close parentheses. How would you say that?
Well, let me make sure I have it right. Like that?
Yes, sir.
Okay.
Equals 0.
Okay. And the minus 1 is not inside the argument of tan?
No, sir.
Okay. So, again, let's approach this algebraically. Most fundamental principle of algebra says that if you're multiplying a bunch of things together and they're equal to 0, one of them has to be 0.
Yes, sir.
So how are we going to solve this?
Set the tangent of x equal to 0, and for the other factor, the tangent of x is equal to 1. Or tangent of x minus 1 equals 0.
That's fine. Yeah, I gave both solutions. Now we have to figure out where those occur. Where is tangent 0?
At 0 and 180 degrees.
And of course, right? I think I have it right.
Yes, sir.
Dot, dot, dot. So how would I express that in this special notation?
0 degrees plus 180 in, or K180.
What does your class use? Do they put the K in front or after?
We put it after.
Let's do that. And do you use N instead of K?
We use in.
Let's do exactly what you do. It's been a while since I've done these. I couldn't remember whether the number goes in front or afterwards. That should cover all answers.
For tangent equals.
Well, no, excuse me, for this part only.
Yes, sir.
And that's not really an answer. You also have to, I forget the notation, but you have to make reference that n is a part of the set of all real numbers, something like that. In other words, this is the answer, not just 180n. Because that doesn't really tell you that n is a positive or negative integer.
Yes, sir.
And I didn't even write it right. It's not all real numbers. It's, I don't even remember this notation. All integers, basically. There is some notation that specifies that.
Yes, sir.
Okay, so let's solve the second part. Where is tangent equal to 1?
In quadrants 1 and 3, 45 and 225.
And again, I think we only need one thing here. What would it be?
45 degrees plus 180 in.
Yeah. Makes me wonder about that first one we had. Well, we can visit it. I seem to remember that most of these you end up having to put 2 rows down in your answer. But what else you got? Maybe we'll run into one.
Yes, sir. Let me see. The secant of x times the cosecant of x minus 2 times the cosecant of x is equal to 0.
Like that?
Yes, sir.
Okay. Thinking algebra again. What can I do here?
We can factor out the cosecant of x.
Yeah. That very first step on these trig equations is always an algebraic one.
Yes, sir.
In other words, not trig, it's just algebra. I do that right?
Yes, sir.
Okay. Now what?
Now we set the cosecant of x equal to 0 and the secant of x minus 2 equal to 0.
Let's just graph these, at least one period of them.
Oh, and this is from the interval 0 to 360.
Oh, okay, good.
So this is just the unit circle.
Okay, cool. Cosecant sits on top of the sine, so we know that it's got to be on top of the peak of that sine curve and on the bottom of the valley of the sine curve, and that's 2 pi. So, what's the solution to that?
The bottom of the valley of the sine curve. So
What we're looking for is where is cosecant x equal to 0?
So that's where
the answer is nowhere. In other words, if we're talking about the range of this graph that I've drawn over here on the left,
that's right.
It is never in between 1 and -1. It is always greater than 1 or less than -1. So when you get one of your solutions, in other words, this is basically a quadratic that we factored, and one of the solutions is impossible, that's fine. That's not the one that's equal to 0. It's the other one. Now, let's solve this one. I don't know about you, but the easiest way I know how to solve it is if the secant equals 2, what's the cosine equal?
1 over 2.
Okay. The only reason that's easier for me is because I have all these memorized. So, where is cosine equal to 1/2 in the first quadrant?
60 degrees.
And in the next positive quadrant?
Next positive. So that would be 240.
I'm sorry?
Oh, wait a minute. That would be 300.
Perfect. And that's your only two answers here, because they limited us to the unit circle.
Yes, sir.
We didn't have to add multiples of 360. However, this does demonstrate something, and that if the domain was not limited from 0 to 360, this would be one of those where we would need to represent it with two lines. In other words, I would have to say 60 plus 360n, that's one answer, and 300 plus 360n. In other words, I got to use both lines. I can't cover it with just one. Notice the difference. The difference between those is 240. So if I added 240 more, I get 540, and that cosine is not equal to positive 1/2 at 540.
Yes, sir.
Okay. All right. What else we got?
So we have 2 times the sine squared of x plus 3 times the sine of x plus 1 is equal to 0.
What are we going to think of first when we look at a trig equation?
An algebraic equation.
Okay, so what would you do with this if it was an algebraic equation?
Factor it. So
exactly what we're going to do with this. So how would you split up the sine squared of x?
The 2 sine of x and sine of x.
What are both signs? Both plus or minus signs. What are they?
Both plus.
Both positive, okay. Not
And then 1.
Not much choice on how to factor 1, so this better work. And luckily it does. There's 1 sine of x. There's 2 more. Add them together, you get our middle term. So that is correct. Now what?
Now we set them both equal to 0.
So we got sine of x. I'm going to do the algebra here. Minus 1/2. And we've got sine of x equal minus 1. Correct?
Yes, sir.
Where is that? Is this also a inside the unit circle only?
This is also inside the unit circle.
Yeah, most of them end up always being that. Once they teach you how to do the n notation, they usually go back to just inside the unit circle. So where is that? What angles?
210 and 330.
And the bottom one?
270.
Notice that when it's 1 or negative 1, there's only one answer in the unit circle. There aren't two.
Yes, sir.
When it's 0, there are two. The only ones that have one answer only are when the sine of some angle is either a negative 1 or a positive 1.
Okay.
And there's only one answer. Every other number, there's going to be two answers. Okay. What else?
Okay. The cosine cubed of x is equal to the cosine of x.
Okay. What are we going to do here?
We are going to bring the cosine of x over to the left. So subtract the cosine of x from both sides.
Okay, and then what are we going to do?
Factor that.
Okay, so I'll do both of those steps at 1. What am I left with?
Alright. So we have the cosine of x times the cosine squared x minus 1 is equal to 0.
Okay, there is a identity for cosine squared x minus 1.
Wait, sir, could you repeat that?
Yeah, whenever you can reduce these, that's going to be the easiest way for you to solve it. In other words, if we start with this trig identity over here, most common Pythagorean identity.
Yes, sir.
You'll rarely see it like this, but where you'll see it is in an expression like cosine squared minus 1. So if I do the algebra here, I get cosine squared minus 1 equals minus sine squared.
Yes, sir.
I'm not sure that's necessarily easier, but just to prove a point, let's leave it like that. Okay, so again,
set them both equal to 0.
Okay, so we're going to end up with cosine x equals 0. Let's solve that one. Remember, there's going to be two answers.
cosine of x is equal to 0. So that is 90 and 270.
Now in this case, you still can't. You're still going to need two rows to represent that answer. If it was the whole number line, as long as it's unit circle only, then that's the answer. Okay. The second part, this part here. If I say sine squared x equals 0, if I say negative sine squared x equals 0, well, I can start off by dividing both sides by -1.
Yes, sir.
Taking the square root, I still get this. It's not a plus or minus 0, it's 0. So where does that occur?
0 and 180 degrees.
So all four of these are answers. And I suppose you could, if they asked you for a full spectrum answer, you could say 90n.
90n.
That would take care of all four of these. The 0, the 90, the 180, and the 270. All of which satisfy that equation.
Yes, sir. And could you, because I don't think I might remember this correctly, why is it that you cannot divide, in the first step, why you cannot divide both sides by the cosine of x?
I love that question. In fact, I would have asked it myself. Because a lot of people would make the mistake, instead of subtracting that cosine x from both sides like you did, they would divide both sides by cosine x. Notice you lose a solution when you do that. And the reason is because it's possible that cosine x can be equal to 0. And whenever you divide both sides of an equation by a variable that might be 0, if 0 is one of the answers, you lose it. The best way for me to describe it would be to give you this one over here. Okay? Same exact concept. Let's just talk about it algebraically. I can tell that this has two solutions. It has w equals 0 as a solution, and then it looks like the 1/6 is a solution.
Yes, sir.
But if I make the mistake of dividing both sides by w, I get this. And now I've only got one solution. The 0 solution disappeared. And yet clearly by looking at it, you can tell the 0 solution should have come in. We should have done it like this, like you did it. Now factor it out, and now you get both solutions. You get w equals 0, and you get w equals 1/6. So it's exactly the same principle, whether it's trig or algebra. If you are dividing both sides by something that might be 0, be careful. It'll work, but you will lose a solution if 0 happens to be one of them.
So it gets rid of the
losing solutions.
Okay, so you lose the possible 0 solution.
Yeah, oddly enough, you do. You lose the 0 solution. That's just kind of another more confirmation of why you can't divide by 0.
Okay.
It's one thing when you're dividing both sides of an equation by a number. As long as it's not 0, you're fine. But if you're dividing by a variable, be very careful.
Yes, sir.
Okay, what else?
2 times the sine squared of x is equal to 2 plus the cosine of x.
All right. First of all, it's very difficult to solve trig equations when you have two different trig functions.
Yes, sir. So you want to get them.
Yeah, everyone we've dealt with up until now has only had one that we were able to factor, and we had two things multiplied together equals 0. We were able to solve each one.
Yes, sir.
Now, is there any way I can turn this into a quadratic that is in one trig function only?
Use the sine squared x plus cosine squared x is equal to 1. So you can change sine squared x into 1 minus cosine squared x.
And now that is going to give us a quadratic. Now I'm going to distribute, and then I'm going to put everything on one side. Okay, let's just distribute first. Now I'm going to move everything to the right. So I'll have a positive. Let's say I don't need that 2, do I?
No, sir. Well, you can cancel that out.
Now I'm going to move this over to the right. So I have this. And now I don't even have to factor it as a quadratic. I can take a greatest common factor out. Now I'm back to the same problem that we keep coming up against. I don't think you have any problem doing this. I think once we get to this point, you're good to go. Am I correct?
Yes, sir.
You've gotten every single answer for every one of them up until now. So you're good at figuring out what those angles are when you know that it's equal to 0.
Yes.
So that's the secret here, is to try to convert. We didn't necessarily have to go this direction. If there was a way to convert that to sine, we could have done that also. But that doesn't convert to sine that easily. And it certainly doesn't leave you with a quadratic. Whereas if I convert that to cosine squared, now everything's in cosine and it's a quadratic.
Yes, sir.
Okay?
Reduction. When something talks about reduction formulas, is that just, are those the same thing as power reducing formulas?
Yes.
So,
However, let me add. Very few students are taught these. In other words, they usually stop at this point. I would say about once every 4 years I get somebody that gets into the reduction formulas. They're far more valuable once you get to calculus.
yes, sir.
Okay? And if you're referring to what I think you're referring to sine squared x equals square root of 1, something like this. I might have a plus sign instead of a minus sign. Oh, no, it's sine x. No, sine squared x. Let's see.
I have for power reducing formulas, also known as half angle identities, the sine squared of theta is equal to 1 minus cosine of 2 theta over 2.
Okay, so I don't
Is
need
that something different?
radical sign. There we go. So that's what it is. Now, this is merely an alteration of the half angle formula, or I should say the double angle formula.
Double angle formula.
Yeah, remember the cosine of 2 theta? There were 3 of them, and one of them was
1 minus 2 sine squared theta.
yes. Well, notice this is just an algebraic manipulation of that.
Yes, sir.
Okay. Why Because when you get to calculus, you can't integrate this, and you can easily integrate that. So it becomes a very valuable tool in calculus.
Yes, sir.
Not so much for precalculus. And it's not really this one you need to memorize. As long as you have your double angle formula memorized, you can always work this one out.
Okay.
There's another one for cosine squared of x, because that is, I believe, 1 plus cosine of 2 theta over.
Yes, sir.
And same thing, I don't know how to integrate cosine squared x, but I can easily integrate the thing that's on the right.
Yes, sir.
So that's the only real usage there. I think I need to ask at this point, are you like self-teaching at this point? Or are you getting your curriculum from a class still?
Most of it is from
Either one. It's helpful for me to know.
a class.
Okay, cool. So they are teaching you this. I do definitely want to cover anything they're teaching in a class. The reason it's a little problematic to self-teach is because all levels of math have degrees of difficulty that go up to almost infinity, including Algebra 1, Geometry, Trigonometry, Precalc, all of them. And
Yes, sir.
it's difficult if you're self-teaching to know what degree of difficulty to go up through.
Yes, sir.
It depends on what you're trying to accomplish. If you're just trying to learn math on your own, well, that's different than if you're trying to pass an SAT course or get into college and be an engineer. So it would only matter in that regards. So we can do some of these if you want. Do you have some specific problems that use the power reduction formula?
I thought I did. Maybe I just misread these. Hold on.
Trying to think of what those problems would look like. Guess they might say, well, I don't know. Let's have a look at them. If not, just go to your next type problem and let's have a look at that one.
Or this might be one. For an expression for cosine to the fourth power x, find an expression for cosine to the fourth power x that does not contain powers of trig functions greater than 1.
Okay. Oh, what's wrong with cosine x times cosine x times cosine x times cosine x? That doesn't contain any trig functions greater than the power of 1. Does that violate their rules? I don't think that's what they're looking for.
Yeah, I think they want you to use the power reduction.
Here's what they're looking for. We will start there.
Yes.
Now they're wanting you to plug in what we know that to be. What is this again? Cosine squared x? In terms of double angle? Cosine double angle?
That is 1 plus cosine 2x over 2.
And now you're beginning to realize why there are 3 trig identities for the double angle. Cosine double angle only. Notice not so much for the sine. It only has 1. But that cosine double angle had 3, and it's all about this.
Yes, sir.
I think that satisfies their request. I don't know. Read the problem again.
Find an expression for cosine to the fourth power x that does not contain trig functions greater than 1. So, yes, I think
Actually, the first answer was also a correct answer, I think. Right? Cosine x times cosine x times cosine.
I think so.
Yeah, I don't know why that doesn't seem to violate their... this is not a correct answer, but I can certainly break it down into 4 cosines. but I think they were looking for this.
Yes, sir.
Okay.
I think that was what they wanted. Then there were also some problems that were talking about using the half angle formulas.
Okay.
So find the sine of pi over 12. So this is going to be in radians.
That's fine.
Find the sine of pi over 12 using a half angle formula and a sum or difference formula.
Either one?
Either one.
Okay. Well, the one that I can do the quickest is a difference formula. That is pi over 3 minus pi over 4. If you do the math, that's 4/12 minus 3/12. You get pi over 12. You with me?
Yes, sir.
Give me the general formula for the sine of A plus or minus B.
That is sine of A times the cosine of B plus the sine of B times the cosine of A. Oh, plus or minus.
Right. So now let's fill it in.
So we have the sine of pi over 3 times the cosine of pi over 4 minus the sine of pi over 4 times the cosine of pi over 3.
Yeah, and all of those are standard angles. So let's see, that's root 3 over 2 times root 2 over 2 minus root 2 over 2 times 1/2. So what do we get? Square root of 6 over 2 minus root 2 over 2. And that is actually quite a common answer, believe it or not. Whenever these kind of problems.
Is that going to be a...
The reason it's a common answer is because you frequently have root 3 times root 2, so that's where you usually get the root 6. Now, there's another way to do it. Let's look at the other way. Let's use the half angle formula. Let me think about this for a second. So we have to double this. So we want, first of all, we want to write this like this. Okay?
Yes, sir.
And I got that by doubling the angle. Instead of pi over 12, double it, you get pi over 6. So this is the same thing as the sine of x over 2. And what is the half angle formula?
The sine of 1/2 theta is the positive or negative square root of 1.
Start from the beginning again. I didn't hear all of what you said.
Plus or minus square root of 1 minus cosine of theta divided by 2.
Okay. Now let's plug it in.
So we have...
It's cosine of pi over 6. In other words, this is x. Right?
Okay. Root 3 over 2.
All divided by 2. And before we go to the next step is going to give us this answer down here. I think. I'll have to think about that in a second. But first of all, let's talk about the plus or minus. Which is it? Which one
That
can
is
we eliminate?
going, sir?
Which one can we eliminate?
The minus.
Right, because we know that's in the first quadrant.
Yes,
So,
sir.
since sine is positive in the first quadrant, we're going to eliminate that negative sign. Now,
Yes,
is
sir.
that the same answer? What do you think?
The same answer as if it were negative?
Doing it by plus or minus way. In other words, we did this a different way. We did this using the half angle formula.
Oh.
Are these two answers the same? Is that equal to that?
That is.
It is equal to that. It's a little bit of sophisticated algebra, but what you basically have to do is, starting with this, multiply top and bottom by 2, giving you this.
That's right.
Hold on a second. Let's see, if I multiply top and bottom by 2, that's what I get. That's what I get on the top. And if I multiply the bottom by 2, I get 4. Hold on, where did I screw up here?
Would you have to multiply by the square root of 2?
Well, the reason I wanted to multiply top, here, I did it wrong. Here. See, on the lower right side, the denominator is not the square root of 2, it's just 2.
Yes, sir.
Whereas in our answer, the 2 is inside the radical. So
Yes,
I wanted to get it outside the radical. So I multiplied top and bottom by 2. That'll turn it into a 4. And then I can take it out as a 1/2, which is the way it is on the right side.
Mm.
In other words, the square root of 3/4 is the square root of 3 over 2. I can take that 4 out as a 2 in the denominator.
Okay.
Okay, so, however, still doesn't seem to solve my problem. Let's see. I have to multiply top and bottom by 2. Here's what I get. 2 minus root 3 over 4. And
Yes, sir.
now I can take the 4 out. Interesting. So in the top, I have this. And what's interesting to me is that has to be the same number. The only difference is this has a double radical. This has got a radical inside of a radical. But somehow these two are equal. I think I can prove it. This is just mildly interesting. I'm not sure I've ever done this exercise before. But so here's the point. Is this the same as this? Right? That's the question.
Yes, sir.
You have to square both sides. So square the left side, you get that.
Yes, sir.
Square the right side, you get 6 minus 2, 12 plus 2. And this becomes 6 minus 4 root 3 plus 2.
Yes, sir.
So that becomes 8 minus 4 root 3. And this is 2 minus 4 root 3. One appears to be a factor of 4 bigger than the other. No, No, this is just 2 root 3 over here. Ah, yes. Now I can divide both sides by 4, and I do have an equation. That is equal to this. That is equal to that. So I just proved that that answer is the same as that answer, even though it doesn't really look a whole lot like it.
Okay.
It's
Yes,
a very
sir.
unusual representation. Certainly at this level of math, you rarely see a radical inside a radical.
Yes, sir.
We don't have that over here. We got radical 6 minus radical 2, all divided by 2. But over here is a whole different story. And I'm not sure how one would go about simplifying that. In other words, if somebody said simplify that thing on the left, I'm not sure I would know how to do it. I don't know how to get rid of that radical in a radical.
Yes, sir.
That's how rare it is in math. It does not come up very often. So I guess one moral to this story is that use sum and difference if you have a choice. You don't end up with radical and radical answers.
Yes, sir.
And as far as how I knew that pi over 12 was pi over 3 minus pi over 4, I've just been doing it so often that I know.
Wow.
So that's something you could work on it, and an easier way to get that is if you use degrees. In other words, that's 15 degrees. And if I'd have said 15 degrees, you would immediately thought 45 minus 30, right? So
Okay.
with 10
Yes, sir.
degrees, it's a lot easier to take these things and separate them into a sum or difference.
Yes, sir.
All right, Garrison, I will let you go.
Yes, sir.
We're on again for Thursday at 3:30.
That's right.
Okay, thanks. Have a good evening.
You too.
Talk to you next time.
Is it 3:30 or?
That's what I've got down. It's 3:30 my time. I think that's 4:30 your time.
Okay. Okay.
Yeah,
That's right.
it's I've got you scheduled for 4:30 your time for the rest of till the end of May.
Yes, sir.
Okay?
All right.
All right, Garrison. Bye-bye.
Have a nice day.
You too.